Hello, everybody. All right, we're done with the numbered chapters. Now we're in the second part of this book, part two, which is II. I'm using Roman numerals now, which we can handle that. So let's get started on it. It's called Strategies for Selecting, Modifying, and Combining Risk Management Methods. Introduction. We cannot solve our problems with the same thinking we used when we created them. That's good advice, and it comes from a pretty smart guy, Albert Einstein. Risk assessment, is it a science or an art? Well, for the authors, it's a combination of both. Risk assessment requires certain skills, knowledge, and experience that are rooted in system safety. However, it also requires imagination and creativity to successfully anticipate, recognize, assess, and treat existing and potential risks. The ability to properly select, customize, and combine methods to assess operational risks provides OSH professionals a certain advantage and value to the organization. With the great amounts of diversity and span of risks that are encountered by organizations, OSH professionals must be able to determine which tools are most appropriate for the level of complexity and the intended audience. To be successful, the occupational safety and health professional must be somewhat familiar with the available methods, their strengths and weaknesses, as well as their application. In this section, a review of risk management methodologies is provided, along with guidelines for selecting, modifying, and combining methods to achieve acceptable risk. Methods available. The number of risk management methods and tools available to the OSH professional is somewhat overwhelming. In other words, there's a whole bunch of them. Many methods are variations of a theme used in the various industries or situations. So like we have seen how many hierarchies of controls are there. They all kind of have the same principle, but they are variations of a theme. And in reality, you got to just pick one that's right for you or your organization. Certain tools have specific applications or purposes, while others are more broadly applied. Some methods are only useful in specific elements of risk management, such as the identification or treatment, while others have a broader application in the process. Now, you see this big heading up here in capital letters of the name of this chapter, and I don't like that, so I'm dropping it for the rest of the show here. Okay, this is going back to our good old process clause 6, which just comes out of what the ISO thing on. We've been through all this stuff. Okay, so we're not now we're looking at some of these tools that are available here. So, in addition to ISO 31010, other risk-related standards that identify risk assessment methods include ANSI ISSE Z590.3, Prevention Through Design, and ANSI Z10, Occupational Health and Safety Management Systems. Table 11.1 provides a comparison of risk assessment methods listed in the 3 standards. Now, these are 3 different standards that have all these different methods in them. And that's kind of daunting, but strangely, I think that there's only one method that's in all 3 of those. And you can see right here, it's right here, checklists. And I like checklists. And that strikes me as pretty strange that all these other ones, there's only one of these 3 organizations has it in there, 1 or 2. You'd think there'd be a lot of them that they'd all agree upon. So you can see how risk management is not, it's still probably in its infancy, because there's not a lot of consensus on type stuff like this, which you would think there would be. I would think there would be anyhow. So Table 2 provides a coded scale for applicability to each component of the risk assessment process for methods covered by ISOs, these 3 ones we just talked about. And the essay, or it says they're strongly applicable, is in green, applicable is in yellow, and not applicable is blank. So here's all different methods, and here's whether they're applicable to these different areas. Hazard risk identification, and then here's your risk analysis, consequence, probability, risk level, and then risk evaluation. Like a job hazard analysis is hazard risk identification only, as is brainstorming, structured interviews, Delphi, checklists, preliminary hazard analysis. Although, again, it's kind of hard to put each of these into in that specific an area. But there's a kind of a guide for you there. This is the same thing. There's a lot of things you can use, a lot of tools out there. But if you can, how much time can you spend learning all these tools? Because you're not going to use all these tools. You might use several of them, but you're certainly going to use the hierarchy of controls and the risk matrix. No doubt about that. In fact, a lot of these use that. So make sure you have a real good foundation and knowledge of the risk matrix and hazard hierarchy of controls. To me, they're the whole basics of risk management is in the area of health and safety for your company. Applicability and complexity of methods included in this manual here. Again, like last one for this one, plan, do, act is the chapter it's in right here. The tool number, they're all numbered in all the chapters. We looked at them. And so communication, context, risk ID, risk analysis, evaluation, risk treatment. And then there's the complexity. Plan, do, check, act model is pretty simple. Risk-based decision-making, moderate. And some things like the layer protection analysis gets kind of complex. FMEA, failure mode and effects analysis, which I didn't think was all that bad. Delphi technique is pretty simple. Pareto analysis is moderate. I think it's pretty simple too. Those are some good ones we have discussed, and I hope you've learned them, what they are. And here's more of them here. Risk indices is pretty simple. And risk treatment tracking, I don't think that's moderate, but I think it's pretty simple. But key performance indicators. Key performance indicators probably has those. They might not call them that. That term has come about, I don't want to say relatively recently, but it wasn't around when I first started in business, put it that way. But it just key performance indicators is basically goals. So criteria for selecting methods should include the process steps, the application, the complexity of the system, criticality of the exposure, output necessary to make decisions, and the resources available. Selecting a risk scoring system. As discussed in Chapter 3, a risk scoring system is used to provide a standardized way of measuring and comparing risks. Such a system provides a consistent and reliable method of risk scoring output that is used by decision makers to manage risk. Now, these are risk management tool selection considerations on these different steps. Process step, application step, hazard exposure, criticality, output, resources. So selecting a risk scoring system. When selecting a risk scoring formula and system, the following variables, which are briefly described, should be considered. A qualitative system. Qualitative risk models are based on qualitative or subjective descriptions and define risk factor levels using descriptive words such as high, medium, and low, which are evaluated according to qualitative criteria. These are often used for quick determinations or low criticality situations. Semi-quantitative systems use qualitative data that is expressed in numerical ratings using a formula to produce a risk score. You know what you're talking about here is basically a risk matrix. You use qualitative data like low, then you give it a number. That's transferring a qualitative to a semi-quantitative. Advantages of semi-quantitative models include the ability to provide more precision in definitions by including numerical ranges for severity and likelihood, as well as the ability to more easily compare and communicate risk levels. Such semi-quantitative values are determined using qualified judgments and experience and do not rely on quantitative data, which is often difficult to obtain. Quantitative systems, true quantitative risk scoring models are rare, since the degree of statistical data and resources necessary to support the quantitative analysis is difficult to obtain or justify. Such models are generally used for high criticality risks where such information is available. So basically, in this course, we're not even going to use them. Two-factor system. Risk factors are their variables used to measure a risk and produce a risk score. Such factors generally consist of severity of harm and likelihood of probability or probability of occurrence. Common two-factor risk calculation systems use likelihood or probability of an event occurrence and the severity of consequences to determine risk level. The risk factors can be multiplied or added to produce a risk score. All right, this is nothing new. This is basically the two axes of your risk matrix. Nothing new here. Multiple factor system. More complex systems using 3 or more risk factors are sometimes selected to incorporate specific factors such as frequency, failure detectability, or control effectiveness. Some of the risk factor variables include exposure, E, which is the abbreviation used for it in their they give you the formula: measure of exposure events, units; frequency of exposure, the number of exposure events per unit of time. And generally these things are, even though they're not written down, they're generally considered when your likelihood is if the exposure to this particular hazard is once every year, then the likelihood is probably pretty low. But if the exposure is 100 of people walking by it every year, then your exposure is going to be really high. So frequency of exposure is a factor in the exposure, of course. Time of duration of exposure. There you go. Time period that a single exposure occurs. Vulnerability, weaknesses in the system that are factored into the risk estimation. Detection of failure, estimate of how easily the potential failure can be detected prior to its occurrence. Now, not when it happened, but prior to it happening. Control reliability, the reliability of a selected control into the risk estimation. Prevention effectiveness, the control's effectiveness in preventing a failure from occurring, and avoidance ability to avoid exposure. But again, like prevention effectiveness, you have a machine that has moving parts on it, you stick a guard around it. The guard's well done, properly secured, think about it. So its prevention effectiveness, control reliability are all pretty high. I mean, it would take something really odd or an effort beyond the reasonable person would do to get by that guard. You could cut it up, you could take a saw to it, of course you could, but that would be really just extreme effort. That would be easily detected. That would be detected easily. Comparison of risk scoring formulas. Various risk scoring formulas and systems are available from operational risk management consensus standards, guidelines, institutes, and books. The following scenario is applied to several different scoring systems to illustrate the similarities and differences of systems. So here's just the scenario they're going to give us, and then we're going to look at the scenario through various different scoring methods. Plasma cutting welded parts, okay? Using scenario factors, the electrical shock hazard is first assessed without controls at a catastrophic severity category 1. Now, remember this risk matrix we're going to use uses 1 as the high side. I don't like it, but that's what they're using. Category 1's potential for death, and a probability level category B. Now they're using, we'll show these in a minute, letters and numbers, which is okay, resulting in a high risk level. Considering the existing single engineering control grounding, the risk is assessed as a severity category 1 and a probability category C. So in other words, that's the 1B is without any controls, and the 1C is with grounding as a control. So the resulting risk residual change, no change, is still a high risk category. As you'll see, this next slide introduces another matrix. This one we just talked about uses letters and numbers, with low letters and low numbers being the highest risk. Kind of unusual though. It also throws in a brand new category, F, eliminated, which is fine, but I think it's a bit redundant. If something is eliminated, it's not even there, so you can't be assessed. That's just my opinion. The particular risk matrix in use is generally not critical, but it is one of the things that should be settled in the very first step, establishing context. This is just me, so I don't forget what to say. Okay, this is the one that we mentioned before. This is the scenario 1, plasma cutting welded parts, and you can see on this risk assessment matrix is 1, 2, 3, 4, 5 is a 6x4 odd. Usually, like I said before, I like the 5x5. I like that 5 because sometimes you get something in the middle, and it could go either way. But they're both catastrophic. So in other words, if something is deemed catastrophic, and this is the same for all of them, just different way, different, just the higher numbers. I think the high numbers should be you're more dangerous than the low numbers, but they're not even using numbers here because this is a qualitative type of thing. So you get a 1A, it's frequent, but if your catastrophic severity is a 1, well, it has to be down there, a remote probability for it even to come down to serious, and improbable for it to come down to medium, because let's face it, somebody getting killed is very, very, very serious. That is catastrophic. So that's this risk matrix. Here comes another risk matrix. This one is qualitative. I'm not sure how they arrived at a residual change of 75% from high to medium. We'll talk about this a little further too. And then we're actually going to get into and go look at this again when we get into the examples at the end of these chapters. All right, so here you go. Probability of occurrence or harm, very likely. I don't like to hear about 1, 2, 3, 4. It's a 4x4. Severity of harm, catastrophic, serious, moderate, minor. So using the scenario, the exposure is assessed without controls and rated catastrophic severity and likely probability. The risk is high. So right here. Now, considering the single engineering control grounded equipment, the range of catastrophic severity and unlikely probability, so it goes down to medium. Now, in this particular one, it's going to go to medium. And the first one still was a high. And risk change is 75% from high to medium. I don't know how they could even do that because there's no numbers here. So what are you dividing what by to get a percentage? That has me a little bewildered in this chapter here. Their use of that 75%. Okay. We'll talk about that again. Here comes yet another MIST matrix. This one is qualitative. They take the risk from a 20 to a 15. Technically, it's semi-qualitative. And it claimed that it's 75% reduction, but I don't see it. Okay, if you go risk from a 20 to a 15, I would call it a 25% reduction because 20 minus 15 is 5, and 5 divided by 20 is 25%. I don't get 75% would. I don't understand it. In fact, they don't use that in these chapters on the case studies that we're going to hit next. But that's what they did. So let's look at it. So this one here has semi-quantitative because that's numbers on, okay? Using scenario factors, the exposure is assessed without controls and rated catastrophic severity level 5, potential death, and likely exposure probability level 4, resulting in a very high risk of 20. Okay. This is only giving you, okay, the severity's down here. It's a little confusing. All right, they're giving it only a 20, which is down here, which is very high risk. 15 or greater is very high risk. All right, 20, and that's their highest, okay. Considering the single engineering control, the scenario is assessed at a severity level of 5 and exposure probability level of 3, resulting in a 15, still a very high risk. Residual change, the risk change of 75%, but still in the very high risk category. So again, how do they get that 75% is beyond me. They don't use that same formula later on. But the next one, they're going to add another factor called protection factor. Next slide. This is the protection factor. You'll see this in the again, but I want to show it here. Elimination is 0.1. And that's amazing to me because if you've eliminated, there should be zero chance if it's there. If it's not there, how can somebody get hurt on it, right? I don't know that one. Substitution, 0.4. Engineering, multiple engineering, 0.6. Single engineering, 0.7. A warning, 0.8. Administrative, 0.9. PPE, 0.95. And no controls, 1. Now remember, these are factors. So when you have factors, you multiply factors. Anything less than 1 is going to make the product less. In other words, so if you have a 2 and you multiply it by 0.9, you're going to get 1.8, right? So anytime you multiply any factor by less than 1, it's going to make that factor less. And the product is, of course, this result with all these factors multiplied together gives you the product or the answer. So, and that's comes about in well, that's just basic math, but comes about in ergonomics too a lot. So we have a lot of factors in your in some of the ergonomic control, I forget what you call them, assessments, ergonomic assessments. So take in mind that the higher number here, the lower number here means it makes it the risk go down. So product's going to be less. And this is really hard to read. So it's in the book on page 248. And this really, it's just a 5x5 matrix. And it just has a lot of verbiage included in here. Like let's look at the marginal medical treatment or restricted work, minor subsystem loss or damage, chemical release. And you see these things here, it gives you some just for people. and the environment. It's kind of like my favorite 5x5 that has this on the side and has 3 columns where you can look at either one of these, that the severity issues. So, so it's pretty close to the basic 5x5. I mean, it's a basic 5x5 matrix. Just has a little more verbiage in it, which is okay, but I kind of like to keep it simple. So there's comparison risk scoring formulas. There's now this just developed by the author. Here you go. Here's the protection factor we talked about, and there's the risk matrix we looked at. So assessing the scenario without controls, the severity levels rated catastrophic of 5, the likelihood of 4, and protection factor of 1, because there's none, resulting in a very high risk level of 20. So 5 times 4 times 1 times 1 times 1 times 1, how many times you want to go? It still is 20. Considering the single engineering control, the scenario is assessed with a severity level of 5, a likelihood of 4, that's 20, a protection factor of 0.7, resulting in a high risk level of 14. Residual risk change is 70%, reducing the risk category from very high to high. 20, okay, whatever. We'll do that again. But you can see that they're just throwing in a protection factor. Now, how do you get it? I don't know how they arrived at those numbers. They look somewhat reasonable. I mean, and just ranking them, they ranked properly. I mean, you're obviously elimination is going to be your best substitution. 1 engineering control, 2 engineering control is pretty close, but warnings, you're going to throw that in. Administrative, I don't know how a warning could be better than administrative. I don't. PPE, not very much help on PPE there, but that's probably not too bad as they go when you start digressing from this. But that's another system. Okay, so you seen several different ways of measuring the same thing. That's what they're trying to point out here. While there are many methods and tools to choose from, it is rare that any are used without some degree of customization to fit the needs of a specific application. Every risk management tool has certain variables, including strengths and weaknesses, that can modify to optimize effectiveness and serve the organization's objectives. Certain characteristics may be missing in a method that, if were present, would increase the method's effectiveness. Such weaknesses or missing components can be opportunities for occupational safety and health professionals to incorporate enhancements or additions to tools in addressing risk management needs. Example 1, job hazard analysis and job risk assessment. This is modifying the methods again. A simple example of customizing a commonly used method follows. Job hazard analysis is a hazard analysis method that can be upgraded and modified to a job risk assessment. So we'll look at this. So this is the job hazard analysis. And we're not going to read everything, but it's pretty approach load and place forks under pallet. Potential hazards, pedestrians struck by. Structures, equipment, and tanks struck by. So they're worried about somebody running something on a forklift. Okay. The recommendations are trained operators. Follow forklift training. That's a little redundant too. If you train your operators, I mean, you have to say follow your training. Approach load slowly. Keep forks 6 inches above the ground. I don't know how that's keeping your load 6 inches above the ground. It's going to stop you from running into something. But that's what they say here. So there is your job safety analysis they've done. Now, they're going to take this job safety analysis and now they're going to take that, well, as you would do in a job safety analysis. I don't want to move that out here. You take the step, you identify each hazard individually, and you rate them each. Now they're going to be struck by or crushed by a forklift. That's pretty severe, but not like it isn't too bad. They're going to give it a 10. The controls, they're saying a spotter or clear area. Well, if you're going to have a spotter every time you drive a forklift, you're probably going to have a lot of business. You have a lot of forklifts. If you only have 1 forklift and you don't use it very often, then maybe a spotter's a good idea. But if you got 10 forklifts, you're probably not going to have 10 spotters. Clear area. All right. Hazard drop load. Limit stack 8 to 4 pallets. Slowly pick up load. There's there. Okay. Now you get drop load. Now you can limit it. That's a good idea to limit the height. Just the higher you get, the less stable it is. So there's the hazard. Now lift load and transport to staging. The hazard there struck by forklift again. Okay. And severity is 5 and 3 now. They're saying it's more likelihood there. Okay. Could be. Again, spotter, clear area, travel with load trailing and blocking view. That's just your forklift training. Rear view mirrors, concave mirrors, emitters, I think they made mirrors. Backup alarms are good. Warning lights are good. Sound horn, eye contact. Eye contact is the best. If you make eye contact with the operator, then you're sure that they see you. You see them. Anyhow, so that's summer controls. Again, the spotter thing is going to be is great. I mean, but it's, you have two people who drive a forklift. Now, struck by falling load, 5 on the 3. All right, controls, load 6 inches off floor. That makes no sense to me whatsoever. I mean, the operation is to lift the load, put it on a pallet, lift it, and transport it to staging. Oh, lift and transport. Okay, you're transporting it. So, okay, I get it now. If you're leaving it, if you have it up in the air, keep your load, you can 6 inches off the floor, you can't get hardly struck by a falling load unless you're really tiny. Travel slowly, no sharp turns or stops, spotter, clear area. If I have forklift drivers, I mean, I would just assume they're following their training. That's why you have it. So lift, load, the height of stack, and place. Now there's your probability of a drop load. Okay. Severity 2, likelihood's 3. Ooh, severity only 2 for a drop load. Limit stack to 4 pallets, slowly pick load. Struck by falling load. Oh, okay, there's your 5. Drop load, hazard. All right. So you can drop the load while it's traveling, I guess. Struck by falling load, 5 and 3. Okay, keep area clear. No spotters there for some reason. I think that's what you really need, a spotter. But keep the area clear. All right. So they're taking a job safety analysis and throwing in the hazard analysis too. That's good. I like the theory behind that. So let's move on to the next one. Example 2, preliminary hazard analysis and preliminary job risk analysis. According to ISO, PHA was preliminary hazard analysis. Whoops, I'm going the wrong direction, aren't I? Screen there. There's a simple method used to identify PHA. They're calling this a preliminary hazard analysis. It's a simple way to use to identify hazards and their risk early in the development of a project, or to prioritize hazards and risk for further analysis. One of its strengths is the use of a before and after controls risk estimation. PHAs provide a comparative analysis of pre-control risk level and post-control risk level assessments for hazards associated with each task that helps communicate the importance of controlling high-risk tasks and applying available resources where they are most beneficial. The comparison of before and after controls reveals the importance of following prescribed measures and controls. This modification can be added to other tools. One such example is a preliminary job assessment, illustrated in figure 3.6. So what they're saying is kind of what we just looked at is a good way to add on to things. I don't disagree with it. Not that it matters. I didn't write the book. Anyhow, okay. Job risk assessment. This is hard to read too. So, but the thing that they've got the initial risks down here, a whole bunch of them are in red, and which means they're high. And then these are the controls, and it lowers them down to none of them are in red. Okay. So that's task hazard. I can't see what that says. Anyhow, that's a good idea too. It's kind of like the same you just did. You have all these, you assess it, and then you put additional controls in it, and you assess it again. That's called you still have this over here. It's called your residual risk. You still have some risk, but it's the risk after you've applied all your controls. Bow tie analysis with risk scoring. One method that has received attention lately is bow tie analysis, partially due to its ability to show the whole picture of a specific hazardous event. A conventional bow tie analysis is a combination of fault tree analysis, the left side of the bow tie, and event tree analysis, the right side, used to provide a clear illustration of the risk pathways and control measures in place for situations that do not require a full quantitative fault tree analysis. Two shortcomings of the bow tie analysis are that it typically lacks a risk scoring mechanism, and that the effectiveness of control measures is not reflected in the analysis. Higher level controls such as elimination, substitution, and engineering are not distinguished from lower level controls such as administrative and PPE, which can lead to improper decision making. To emphasize the importance of the hierarchy of controls, the example of a modified bow tie developed by the authors is shown in figure 11.9. Now, this is number 3, bow tie analysis with risk scoring. And I'm not going to get into this too much because it's really a lot to get into for this course. So it's in there. It doesn't go into a lot of detail in the book on it, but you have to understand what it is. And this is looking at it from 2 different ways. And then it's hard to read. But that's I see why it's a striped bow tie analysis. It looks like a bow tie. Okay. So they call the other one square analysis. I don't know. Combining methods. Seldom does one tool adequately meet all the requirements of an entire job, whether it's in construction, manufacturing, or the risk management and OSH professions. OSH professionals working with risk management are confronted with various problems and challenges in their organizations daily. The need to not only select and modify tools, but properly combine methods to complete the risk management effort is often required. Simple risk identification or analysis efforts may only require a single technique. Many situations require more than one method. And I'm going to guess what you run into most of the time in your career are going to be relatively simple, not requiring a whole lot of techniques. The methods in this exercise were selected, modified, and combined by the risk assessment team after understanding the needs and establishing the context of the assessment. The methods include, in order, hazard ID and risk ID, hazard and risk assessment matrix and heat map, preliminary hazard analysis of current state and future state, layers of protection analysis, striped bow tie assessments of current state and future state, and a cascading bow tie diagram connecting operational risks to safety, health, and environment risks and resulting business consequences, which are tied to an organization's objectives. So these are combining methods we're going to look at now. And on the left, communication, consultation with stakeholders and decision makers. Now, these kind of the risks. Establish context, assemble the team, establish the context, establish your risk assessment methods. Then you do hazard risk identification, hazard, risk ID, RAM, and heat map. Risk, okay. You're going to identify risk analysis, PHA, current state, layers of protection, striped bow tie. Now, that's just what their example. There's a whole bunch of them in here now. These things you can use. Risk evaluation, cascading bow tie, PHA, future state, cascading bow tie, FS. Risk treatment, risk-based decisions, implement controls, monitor, and refine. So this is, again, the verbiage in here is used very, is sometimes not real concise, let's put it that way. But then these are just some. There's a whole bunch of methods in here in this book, and you can use. Now, this is combined modified methods example. Initial process, establish risk assessment protocols, incorporate risk criteria and acceptable risk level in trigger protocols, determine specific triggers and communicate, review and revise protocols as organizations mature. Okay. Combined modified methods, hazard. So you got hazard operational and hazard safety. Biodiesel manufacturing, methanol tank storage. I think they're going to use this methanol tank storage here a couple times. Let's look at your first hazard. Thermal expansion, methanol vapor generation. The cause, faulty blocked vent, excessive in-tank vapor generation, consequence of overpressurization, loss of containment, property and tank damage. Hazard, physical vapor generation, ignition, consequences, explosion, property loss, workers are exposed. They're combining these for some reason. Okay. Faulty blocked vent. There's no controls yet, and they're just doing this. Okay. Corrosion, methanol tanks, trim and piping, incompatible tank and trim materials. Okay. Remember ragging up? You wouldn't have this if you follow ragging up. Incompatible tank and trim materials. That would just be and the process safety management, you just wouldn't do that. I mean, if you followed it. Loss of containment, methanol product loss. Hazard to chemical, methanol workers exposed. Blindness, headache, nausea, weakness, or consequences. And it goes on. Combined modified methods. Now here they're just looking at a couple of these. Calling this risk ID. Hazard 1, physical. I'm going to backtrack a little bit. Hazard 1. Okay, there's your hazard ID. Thermal expansion, physical vapor generation and ignition, consequence, explosion, property loss, workers exposed. So your severity and likelihood are 4 and 3. That gives you a risk level 12. The second one, chemical methanol workers exposed, blindness, headache, nausea, weight is 4 and 2. Severity is 4, likelihood is only 2. Hazard 3, physical chemical vapor generation, ignition, explosion, local population exposure. That's a severity of 5 and a likelihood of 3. So that's a 15. So now here we go. This is like kind of my favorite risk management matrix, what do you want to call it? They're calling it risk assessment matrix. Here you go. Here's your outcomes over here. And here's why I like this one. It's a 5 by 5, and I like that because it gives you kind of that mid range. And there's a severity rating over here, your likelihood up here, and health effects, property damage, environmental impact. And so most hazards are only going to fall into one of these. But if it's a release of a chemical, then you're going to have environmental impact and maybe property damage as well. So you might want to have, you have to include all this. You might want to do a separate one for each one. But so that's what I kind of like about this. And it's relatively simple. And as you know, I follow the KISS method, keep it simple, stupid. I try to keep it that way. And this one is pretty simple. And I think it has enough in there, though, to be useful. So, and then they're taking these things and they're throwing on this heat map. Hazard 1, hazard 2, hazard 3. Hazard 1 and hazard 3, as you can see, I'll back up a little bit. Oops. I got the wrong way, didn't I? Where did I go? Well, I backed up a lot, didn't I? Okay. Hazard 1. Okay, there's your hazard 1, 2, and 3. Okay, corrosion. All right. And hazard 3 was human factor error to overfilling, methanol product loss, physical, chemical, vapor generation, ignition, explosion. All right, there we go. All right, that's pretty serious. All right, the heat map, there you go. It's just these three, 12, 8, and 15. That's all these are. 4 times 2 is 8, 4 times 3 is 12, 5 times 3 is 15. So that's your numbers there. Do you have to put them on that? I mean, you can see the numbers. Why do you need to put them on this heat map? I don't know. All right. Combined methods, risk analysis, PHA example. These are, here you go. They're one day and they give them 3, 2, 1, and 2 now. Thermal expansion again here on number 1. Methanol tanks in sun causing internal pressure buildup. Expansion vent on top of tank. Now, this is a classic example of prevention through design. If you have a methanol tank and you know that the sun is going to heat up and expand it in that tank, why do you have another sun? I mean, wouldn't you put it somewhere? It depends on where you're at, especially if you're in California, where most of your heat comes from the sun. And so you'd think that you would have it in the sun. Anyhow, exposed assets, employees, contractors, product loss, process, total community involvement, local community involvement. Existing controls are tank vents. And so now that gives you 12. Now, when you have a tank on a pressure vessel and you have a vent on it, I don't know how it is in most states, but every state I've been in, that's considered, that comes under your, what they call it, your boiler. They call them the boiler, but any pressure vessel, usually your Department of Labor in your state has a boiler inspector or a chief boiler inspector, and then they farm that out frequently to insurance companies because the insurance companies have a dog in that fight, and they have licensed, certified boiler inspectors, and they come around, they check all your pressure vessels, not just your boilers, your air compressors of a certain size. Under a certain size, they don't, but anything, tanks, CO2 tanks, any kind of tanks. And one of the things they check on that, and believe me, they check it, is your vent. Make sure it works, and that the vent is it blows or goes off at or below the MAWP, the maximum allowed working pressure. So if you have a tank that has MAWP of 350 psi, that vent better be designed to go off at 350 psi or less. And they'll try it. They'll open it. Well, no, that won't be at 350 psi, but they won't open it. They'll make you open it, because if something goes wrong, they got no they didn't do it. They can't mess it up, so they can't influence it. So that's a good idea. Anyhow, so anti-tank, shade protection of a tank, great. Warning, internal pressure alarm. That's a good idea. Admin, mechanical integrity program. You got a vent, you should have a mechanical integrity program, whether it's by the state like that or just on your own. And PPE. I don't know what PPE is going to do for you, but so this is kind of the things that we'll get when we get into process safety management. All right, combined modified methods, risk analysis, and LOPA example. LOPA, layers of protection. So here's your expansion, sun vent failure, independent protection, layered 1, it's tank vents. Current state is 12. Okay, that's kind of like where we're at right here. All right. The proposed additional independent protection layers, IPLs. Shade protection for tanks. All right. Explosion proof equipment. Explosion proof equipment. All right. Internal pressure alarms, good. I don't know what explosion proof. I don't know. I mean, you see how big a boiler is, and it's not explosion proof. Spill containment. Okay, for a liquid, this is a vapor, so I don't know how you can contain it. This is if it's housed in the building, that would be a good idea. Auto fire extinguishing system, that's a great idea. So your severity is still 4, but now you reduce your likelihood if you put all these layers of protection in there. And I like the theory of a layer of protection a lot. I mean, should you do all of these? I don't know how explosion proof equipment they mean there could do, but I never heard of an explosion proof tank. It could be one though. Internal pressure alarm, spill containment. I mean, if pressure gets built up inside enough and high enough in a tank, it's going to blow, and that's why you have pressure relief valves. It might not blow the tank. It might blow the piping if there's type of piping to it too. All right. Anyhow, corrosion, methyl tanks, cathodic protection. That's protection against. I'm gonna sneeze here. God bless me. Thank you. All right. Auto fire extinguishing system. That's probably good. So again, by taking all these layers of protection in there, they're going to assume this likelihood goes way down. And that's probably a valid, if you've done all these things. Now they're overfilling. Okay, distraction, deviation, severity 5, likelihood 3. Okay, they're causing this. All right, very high. And they're making this with an overfill tank, automatic shut off, overfill alarm, auto fire extinguishing system, spill containment, all the way down to 5. All right. I like that one. That's good. I'm not going to get into these striped bow ties. They're just way too. I don't think the time we'd spend on analyzing one of these would be worth it. So you want to look at it in the book, and they won't be on any tests or anything like that. Striped bow ties. Combined methods, cascading bow ties. They like bow ties. Conclusion. Only bow tie I have from a tux. I don't wear it anymore. So there are multiple methods and options to consider when selecting risk management tools. Having access and knowledge of available methods and tools is the first step. Being able and willing to consider simplifications or modifications and improvements to methods is the second step. And finally, the ability to put it all together, selecting the right risk management tools, making appropriate adjustments, and combining the methods to achieve the necessary results is the future of the occupational safety and health profession. But again, in your career, you're probably going to use risk matrix and has hierarchy controls quite a bit, but that's going to probably be most of it. Now, if you get pretty sophisticated, then you have to go into higher things by all means, and you should dig out your book here and take a look at it. And again, I always say this too: don't ever hesitate to hire a consultant. There's nothing wrong. You can't know everything about safety, and there's nothing wrong with hiring a consultant. So anyhow, this was a pretty interesting chapter, I thought. And so we're going to get into some really interesting case studies next. In the meantime, be safe.